Don't rely on it. If things permit, I may share. So, good afternoon to all of you. Let us just begin the first session for our discussion of numerical methods in civil engineering. And the first part will be your methods of interpolation. I hope that slide is visible for all of you. Slide is visible, right?
Yes, sir.
Okay. So basically, in the methods of interpolation, you have in the method of interpolation, you will be having for the equally spaced data, or you can also say uniformly, or sometimes it can be your unequally spaced. Okay, so the methods of interpolation for equally spaced and unequally spaced are different. Okay, what are the most prevalent methods that we'll be discussing for each one of the cases? For the equally spaced, you have Newton's interpolation. This Newton's interpolation, it will utilize your the finite differences. Okay, so it makes use of the finite differences that will be your further subdivided into forward, backward, and central differences. Okay, these will be the three categories that you will be having for the Newton interpolation, and this is for the uniformly spaced data points. Okay, now if you have unequally spaced data points, so for that the categories will be, the methods or approaches will be your the divided differences, then Lagrangian, and Hermitian. So these three are the ones where you have unequally spaced data points. Then you can solve or you can interpolate by means of your divided differences, Lagrangian approach or Hermitian approach. So these Lagrangian approach as well as Hermitian approach, it is very much used when you are studying the finite element method. In the finite element method, when you are covering your the shape functions, etc., when you have to find the shape functions, etc., at that time you utilize the Lagrangian and Hermitian approach. The Newton's interpolation, forward, backward, or central, it is very much used when you have a specific set of data points and you have to find out the value for an intermediate data point. Okay, so there's a independent variable, there is a dependent variable. So how we are going to solve these things, that we will be looking into the chapter. Okay, so this will be your first unit. Let us just see what are the things. So consider a function, y equals to f of x, right? So I believe you all very much clearly know what do you mean by y is here. Can anybody tell me what type of variable it is?
Dependent variables.
Yes, it
Dependent.
is a
Dependent.
dependent variable, whereas x will be your
Independent.
independent variable. So y will be your dependent variable and x will be your independent variable. So that means for any value of x, we have a function by which we would be able to obtain the value of y. Okay, so suppose I have certain set of data points for x and y. So I have certain set of data points that is denoted by x naught, y naught, x1. For x1 you will be having y1, x2, y2, and so on till xn will be having yn. So how many data points you have? You have n plus 1 data points. So you have n plus 1 data points, and these suppose किस type के data points हैं ये? See, if you have suppose a stress strain relationship, and you obtain for particular stresses what is the strain that you have observed in your experimental value. Okay, so that can be one of the data points that will be there. So a triaxial data, or suppose we are having this plate load test. So at a particular application of load, you are recording a particular amount of settlement. Okay, so in this manner we may have certain data points. Now if I want a value to be somewhat in between this space, suppose x dash. Okay, this is x dash. I want to interpolate the value of dependent variable, which will be here y dash. Okay, so I have the data points. I want the value of y dash for a known x dash. So x dash is what? It is known to me. X dash is known to me, and I want an unknown variable, unknown value. I want to calculate the value of this unknown. Okay, so how we are going to utilize the interpolation techniques for doing the same, that we will be learning in this Newton's interpolation. So let us see. If I draw a graph, excuse me if it is not a straight line properly. Okay, so suppose I mark the points. This is suppose y naught, y1, y2, and so on till yn. Or rather, let me take rather let me make some arrangements. Sorry, I'm sorry, I have not marked the axis. Let it be an x-axis and let it be y-axis, then it will be very much convenient. Okay, so mark it as x0, x1, x2, and xn. For each of these values you have certain y values, and if I connect all the data points, I am obtaining somewhat this sort of a curve. And this is what? Y is equals to f of x. This is your y equals to f of x line. Okay, and here okay, at the point x1, I am having this, which is your y naught, This is what? Y1, Y2, and at this I have phi n. Okay. So in this case, if suppose I have to find us for an arbitrary point, suppose an arbitrary point is x prime. For this arbitrary point, I want the value of y, which is unknown. Okay, so here these are n number of, what I should write here is there is n plus 1 data points, n plus 1 data points, and x prime is what? X prime is an arbitrary point in the domain x naught xn. So in the domain x naught xn, you have an arbitrary point which is x prime. And yes, one of the most important point here is they are all the data points, it is equally spaced distinct points. So all these are equally spaced distinct points. So what I am doing here, so in basic points, if I write down the definition of interpolation, what do you mean by interpolation? It is a process. What type of process it is? It is a process for predicting the value of a dependent variable. Okay, predicting the value of a dependent variable. Okay, dependent variable, here I am denoting it by y dash, or I can write it down as yi, suppose. Okay, so interpolation is a process for predicting the value of a dependent variable, which is your yi, at any arbitrary chosen point, which is your xi. Okay, and what we are using it through the use of polynomial. Through the use of polynomials. So this is what interpolation means. Now interpolation may utilize a polynomial interpolation. It generally, it is the basis for this is the derivation and everything. Okay, we generally use the numerical differentiation technique. So actually you can say that interpolation, it is the starting point for numerical differentiation, and also it is the basis of all the derivations which are there in numerical integration. Okay, so numerical integration, and what do you mean by numerical differentiation? A slight introduction I provided you in the previous class, that when you utilize a numerical differentiation, when you utilize a numerical integration. Okay, whenever your problem is very much complex and by the exact solution you are not able to obtain the results, so that time you use these numerical techniques, right? So interpolation, it will serve as the starting point for the numerical differentiation, and also it will be the basis of all the derivations or derivation of all the numerical integration formulas. So whatever numerical integration formulas will be there, so this will be the basis of that. Okay, so basically, can you anyone tell me what do you mean by polynomial interpolation? What do you mean by a polynomial Interpolation. I hope that you all are following me, right? Any queries? Am I audible to you all?
Yes, sir.
Yeah.
Yes,
If
sir.
any queries will be there, please let me know. And when you have like 5 minutes left for your class, do notify me. Okay.
Okay,
Hmm.
sir.
So, a polynomial interpolation, what do you mean by this? So, in the polynomial interpolation, we determine the unique nth order polynomial. We determine a unique nth order polynomial. We determine a unique nth order polynomial which fits, okay, which fits to this n plus 1 data points. So unique nth order polynomial which fits to these n plus 1 data points, it is used, and that polynomial that we derive, this will be used for what I should say, for determining the intermediate values. It will be utilized for determining the intermediate values. I believe that you all know how a polynomial can be represented. There are various means, we will be utilizing 2 or 3 of them. But what do you mean by nth order polynomial? If I represent it as a p of x, suppose polynomial, then it will be represented as a naught plus a1x plus a2x square plus a3x, what I should say, q plus dot 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 a, rather, a n minus 1 x power n minus 1 plus a n x power n. So this will be a representation of your a polynomial. Okay. Now if suppose I have, I believe that you all are, if there is a first order polynomial, if there is a first order polynomial, suppose whatever x and y axis, we can represent it anyways. So first order polynomial, what it will be? It will be simply that you are connecting 2 data points like this. So whenever we have 2 data points and we try to derive a polynomial expression, we boil down to a first order polynomial, and this is what it is. Isn't it a linear line?
Yes, straight line.
Yes. So this is what this is, first order polynomial, and it is a linear line. Okay. So first order polynomial, linear line. If you have, suppose, similarly, if you take 2 data points, then whatever polynomial you will obtain, it will be what? Somewhat like this. 3 data points, it will be somewhat like this for 3 data points. And for suppose 4 data points, if we have, okay. And what it will be? It will be a sorry. Yes. Anyways, it will be a second order,
Second order
and you can write it as parabolic,
parabolic.
right? The term will be your x squared, right? And then your third order polynomial, third order equation, it will be your cubic. Yes. So these are the basic ideas that I wanted to impart you about the polynomial. What do you mean by a polynomial expression, etc., and etc. Right? Now, what is our aim? Again, I am mentioning the aim. Our aim for this particular learning, it is to predict yi at any xi so long your xi lies within the domain. Right? That is your. So this we have discussed. Okay, when it lies within the domain. Fine. So this is our aim. Now let us just see. Sorry. Let us now start after getting a brief idea, basic introduction about what do you mean by various terms and terminologies that we are going to use in this particular unit. Let us just go for the Newton's interpolation. Newton's interpolation, which is for uniformly spaced data points. Yes. This basically, it makes use of the finite differences I mentioned, and there are A, B, C, as I have mentioned in the previous slides as well, that forward difference, backward, and your central difference. Fine. Here, suppose let us now discuss the first one, which is your forward difference. So what do you mean by forward difference? The first forward difference for a function y at a point x. How we are going to define that? So basically, if you represent the data points, suppose I, this is the I data point, then at an equal space, let it be represented as h. Okay, so we have I plus 1, then again we have I plus 2, I plus 3, I plus 4, and so on and so forth. I can move on and on. Okay, how we are going to write? So your first forward difference of function y at any point I. How I am going to write it down? So this is the, see, should write it down here itself, that delta, this delta, it is the forward difference operator. This will be a forward difference operator, right? And how I am going to write down that delta yi, okay, this will be, can anybody, I believe that you all have a slight idea about this as well, because this is a basic part, right? So can anybody tell me what will be delta yi for forward difference?
yi plus 1 minus yi.
Yes, very simple. yi plus 1 minus yi. Okay. Similarly, if I move on for the second, it will be simply this delta yi. Again, you can go for this yi plus 1 minus yi. So individually, you have to apply this particular equation. So this will be what? Yi plus 2 minus yi plus 1. Okay, minus yi plus 1 minus yi, which will be in turn resulting into yi plus 2 minus 2 times yi plus 1 plus yi. Am I correct? In the similar manner, you can obtain for the third order as well. What it will be? Yi plus 3 minus 3 times yi plus 2 plus 3 times yi plus 1 minus yi. And most of the times we utilize for the fourth one as well. So it will be what? If you go on in the similar manner as we have obtained for the second order operator, so it will be your yi plus 4 minus 4 times yi plus 3 plus 6 yi plus 2 minus 4 yi plus 1 plus yi. Okay, and if we go on and on with this, if we go on and on with this, we would be able to like obtain a generalized expression for it. So a generalized expression, what will be a generalized expression for it? Suppose if I have nth order operator for the forward difference, how I will be writing it down? I plus n. If you just look into the pattern, wherever you had 2, okay, you had I plus 2 here. Okay, in the similar manner, when you have nth order, you will be having I plus n, then alternate plus and minus will be there, n times y I plus n minus 1, right, plus n into n minus 1 upon 2 factorial y I plus n minus 2, and so on and so forth. And in the intermediate, we can mention that suppose at any point k or any other k, suppose that minus 1 by minus 1 k, the term kth term, nck, okay, combinations y of I plus n minus k, and so on. Okay, so this will be for any generalized nth order forward difference of y at any point I. Nth order forward difference for y at any point I. So this is how we generate this forward difference. So if I want to obtain the forward difference table, if I want to obtain the forward difference table, okay, there will be here x, y, okay, then the first order, second order, third order, fourth order, and so on and so forth. We can go on and on. Here I have the data points x naught, y naught, x1 corresponding y1, x2 corresponding y2, x3 corresponding y3, x4 corresponding y4, and if we move on and on till xn, there will be yn, right? So in generating this table, rather than utilizing the generalized expression of forward difference, it is very much simpler if we do it by a very simple technique. If we take first one is very simple, as you all know. If we take these two, then this will give you what? Delta y naught, which is what? Y1 minus y naught. Yes? In the similar manner, from these two, I will be having delta y1. By these two, I'll be having delta y2. From these two, I will be having delta y3, right? Now again, second time when I do it, as I was discussing with you, if you look into this one, okay, here second order, I have written it delta yi plus 1 minus delta yi also, right? So in the similar manner here, rather than utilizing the expression which is your which will be a quite lengthy, that means y2 minus 2 y1 plus y naught, I can simply, what I can do is I can deduct this quantity from this one. That means this will be your delta 2 y naught, which is your delta y1 minus delta y naught. Okay, similarly for the other cases as well, that means this one as well as this one, delta y1 delta 2 y2. And as I move on and on, again the same process, this minus this, it will result into delta third order forward difference. And again, finally, it will again result into fourth order finite difference, that will be this minus this. Okay, so I hope that you have been familiar with this forward difference table, how you are obtaining this forward difference table, and I am very much clear about it. Okay, yes or no?
Yes.
You all will be able to obtain this forward difference table for a particular data points, set of data points.
Yes, sir.
Yes. Yes. Any queries?
No, sir.
No, sir.
No, sir.
Okay. Let's move on then. So any nth degree polynomial, if I have, for any nth degree polynomial, if I have, suppose Pn of x, okay, I can write it down as a naught plus a1 x minus x naught plus a2 x minus x naught multiplied by x minus x1 plus a3 x minus x naught x minus x1 x minus x2, okay, and so on. Finally, an, it will be what? X minus x naught, x minus x1, and this multiplication product will go on x minus x. As you can see, when we were having 3 here, we have 2. So finally it will be what? If I am having n here, it will be x. Anyone?
N minus.
N minus 1. Very good. Okay. So this is what we will be having for the polynomial. Is it okay? Now, how I can find out these coefficients, a0, a1, etc. So basically, if I have to find a at any of these coefficients, how I am going to find these coefficients? So simply I know the data points, right? Yes, from the data points, I will simply find it out. At your x is equals to x naught, I know that y is equals to y naught. Now I will utilize this polynomial for x naught. What? It will be y naught. And if I use this expression, x naught, simply this will be x naught minus 0 and so on for all the other points. So it will be simply what? A naught. So what I can write it down as your a naught, this is equals to what?
Y naught.
Y naught, which is y naught is known to us. This is a known data point. In the similar manner, at your x is equals to x1, I have y is equals to y1. So what it will be? Pn for x1, it will be simply y1. And if I go on from the polynomial expression, it will be your a naught plus a1 x1 minus x naught. For all other terms, it will be boiled down to 0. Because in the next term, it will be your x1 minus x1. So as the multiplication, the product term, you will be having x1 minus x1, which is your 0. So ultimately, all the other points will be 0. Here, I can further write it down as your y1. What is y1? A naught, from this we have already known is, it is y naught plus a1 x1 minus x naught, a1 y1 minus y naught upon x1 minus x naught. So just you can see that it is also a reminder of your 2-point expression, okay, or linear line. Yes, slope, you know the slope, etc., right? Anyways, from the diagrams that I've shown you, that between 2 points the space equally spaced, we are denoting it with h, and your yi plus 1 minus yi was what? Your delta I. So using these two, I can write it down that a1, it is equals to y1 minus y naught will be your delta y naught, and x1 minus x naught, this is what? The space
H.
between the
H.
data points. So it will be what?
H.
So simply your another coefficients we were able to find out. Now let me look into the another one, that is your at x equals to x2, y is equals to y2. Now if I do it for this one, p, and you all also do it on your own, okay? x2 minus x1, x2 minus x naught. That's it. I believe all other terms will be 0, right? This can be further, we can write it down as your y2 is equals to a naught is what? is y naught. A1 is what? Delta y naught upon h. And x2 minus x naught, it will be simply what? X2 minus x naught. Okay, so it will be what? Two h's. Plus a2, which we need to find out, x2 minus x1 will be what? H, as uniformly spaced, and x2 minus x naught, it is what? 2 times of h. So if we look into this particular expression, here this h and h are cancelled out, okay, and your a2, it will be what? y2 minus y naught minus of delta y naught is what? Y1 minus y naught, yes, upon 2 times h square. What will this be? Y2 there's an issue, I believe. Sorry. This was y naught. This will be your. Oh, sorry. Here it is 2 times, right? Here it is 2. I missed it out. Okay. So here it will be y2 minus 2 times y1 minus 2y naught plus 2y naught minus y naught will be plus y naught. That's what I was thinking. Why I was not obtaining. I missed out this 2. Sorry for that. And this is what? This is the expression for the second order forward difference, right? So A2, it can be expressed as delta 2 y naught upon 2h square, right? This 2, it can be written as a factorial 2. Okay, factorial 2, you will see it, because as we will be moving on, we will obtain factorial 3, factorial 4, and all those values one after the other. So this was for the A2. Similarly, whatever we will be having, like means
A3.
Sorry. So we will be having the similarly we will be having A3, which is what? Delta cube y naught upon 3 factorial h cube. You can derive the same, okay? And if I go so on and on, my an, it will be what? The nth order of forward difference upon n factorial into h power n. Yes. So finally, therefore, what will be my polynomial? The nth degree polynomial nth degree polynomial, what it will be? Pn of x, simply y naught. And as you can see here, we used to have, right? We have written this expression. Just we have to replace these coefficients, and accordingly we will get the values. So
Plus
y naught,
delta y naught by h.
yes,
Plus delta y
plus
naught by h.
delta y naught upon h, x minus x naught,
plus
okay, plus delta 2 y naught upon 2 factorial h square, x minus x naught into x minus x1, okay, plus dot 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 as we move on, delta power n y naught upon nth factorial h power n, and here you will be having x minus x naught, x minus x1, x minus x n minus 1. Yes.
Yes.
So this will be the entire expression, what I should say, for a polynomial expression. Okay, nth degree polynomial. So this is what the nth degree polynomial for a forward difference. So will you all be able to solve a problem with this? Let us just try a problem before we end this class session. I believe we have 5 to 10 minutes. So let us just try one problem. Okay. So what you have is you have to find y at 4.2. This is a query. Okay, this is the question that you have. And what are the data points? Sorry. The data points, that is your x and y data points. So for a value of 2, you have 23. 4, you have 93. 6, 8, 10, 12, and 14. Corresponding values you have 259, then your 569. Corresponding to 10, it is your 1071. 1813, first 1813, and 2843. Yes. So these are how many data points? 1, 2, 3, 4, 5, 6, 7. You have 7 set of data points. What you can do is, our aim is to find y at 4.2. What will be our approach? We will prepare the forward difference table, right? And then we will obtain the polynomial expression, and from the polynomial expression directly we will obtain y at 4.2. Yes. So will it be possible for all of you?
Sir.
Yes. First, second, third, and fourth. You can do the calculations later, rather than, as we have less number of time, I have already calculated these. Okay. So simply this minus this here, it will be what? Your 70. Then this minus this, here it is your 166.
66.
Then 310. Then you all keep on doing on your own also.
502.
502, 742, 1030. Now for this one, we will deduct these, and it will be what? 96,
96.
144,
144.
192. You all also use your calculator, keep on doing it. In the next class, make sure that you install Octave on your laptop. Okay, so that we will be programming, coding this as well. 240,
40.
288.
88.
Okay, again this, it will be your 48, 48, 48. This also 48.
48.
0, 0, 0. I believe now we don't have to move on and on, because or else it can go up till what? Delta power 5, 2 values, then delta 6y,
6.
1 value.
One
So
value.
delta 6y, we can go till delta 6y. So when we are having 7 data points, we can go up to delta 6y.
6.
Okay, however, here it is 0 itself here, so we don't need to move further, I suppose. Okay. So now, if what is my aim? I have to find y at 4.2. So for that, the polynomial expression, I'm directly using it at x equals to 4.2. You can write it down. Now, in practice, what we do is, in practice, as we are going for forward difference, in practice, what we do, we take closer value, which is x equal to 4.2. So we take this value, 4 value, and we consider this one as our x naught, this one as our y naught, and so your delta y naught, it will be this one, this will be your delta y naught, this one will be your delta 2 y naught, and this one will be your delta 3 y naught. Finally, this one delta 4 y naught. However, we won't be using it as it is 0, so it will be of no use, right? So now our expression will be, as I am considering this, so what it was, polynomial expression, 93 y naught plus delta y naught upon h.
Upon H.
H, what is h here?
2. 2.
So it will be simply 2 x, which we have to find out, 4.2
4.2
minus x naught,
minus
which
4.
is what? 4.
4.
Okay, plus delta 2 upon 2 factorial into h square, right?
Yes, sir.
X minus x naught,
6. 4.2 minus 6.
right? Similarly, then next one will be your
48.
48. 3 factorial, that is 6.
6.
Arey yaar, sorry. 3 factorial, that is what? 6 multiplied by
Multiplied by
h cube, that means your 8.
8.
Here it will be again 4.2 minus 4, 4.2 minus 6, and 4.2 minus 8. Yes?
Yes.
So finally, what will be my this? Y at 4.2. What is the value? The value boils down to your 104.48. 102.48. This is the value at y equals to 4.2. Okay, so as you can see here, 4.2, it is just between these two, 93 and 259, and it is an increasing value. So we can say that yes, this value is coming out to be in between 93 and 259, which is your 104.48. So this is how we did the interpolation. If we use higher orders also, if we go on and on, as it is 0, that's why I am not moving on. Or else what happens if our forward difference table is still this delta 6y, and we have some values there rather than 0. So the higher order of forward difference we consider, the higher order of our higher degree of polynomial we consider, our value will be much more precise. Yes?
Yes, sir.
Okay, I'm clear with that? Okay.
Yes, sir.
So with this, let me just wind up today's class. In the next class, we will try to code on Octave. You may install the Octave software. We will try to write a code on Octave for this forward interpolation. And then we will look into backward interpolation and central interpolation and so on and so forth. Okay? Any queries till this portion? Any queries?
No, sir.
Okay, then we will meet in our next class, right? I hope that you all were able to learn things. Let me just see whether the attendance has been recorded nicely or not.
Sir,
Yes.
actually I missed the first class, so is it possible can I get the notes for that?
You missed the first
First
class.
class, yeah.
Okay.